Welcome back, students. Before starting the second subproblem, let's review what we just did in the first problem. Here we go. A radar unit is used to measure the speed of automobiles on the expressway during the rush hour traffic. The speed of individual automobiles are normally distributed with a mean of 62 miles per hour. And the standard deviation for this rush hour traffic is given by 4.95 miles per hour. And here's the question: what proportion of the cars are traveling in 70 miles per hour or less? Well, here is the normal picture associated to that. 62 is the center, 70 is the end, and we shade the left hand side because the problem says 70 or less. And which method did you use? We used z-score formula, n minus center over SD. So 70 minus 62 or 4.95 calculated, we got about 1.62, and using that we looked up the normal table. To the second page, 1.6, so we have to look at 1.6 row as highlighted, and the second decimal digit is 2, so you have to look at this column for 2. We end up with 0.9474. That should be the answer. So approximately speaking, about 95% of the cars are driving in 70 miles per hour or less. Here is a little bit more accurate computation using Mathematica, using more decimal digits, not just 2 decimal digits. We get pretty similar results, as a matter of fact. In the end, of course, just 95 miles per hour, 95%, excuse me. Now, the second problem is asking you about going backward. Find the 25th percentile. We are looking for something like this. This probability here is 25%. So a quarter of the cars are traveling less than this speed. The other 3/4 of the cars are traveling faster than that speed. So it should be a little bit less than 62, because right at 62, you're going to get half and half. So 25th percentile, a little bit less than 62. And we are looking for this x value. This probability is 0.25. How do we get that? We have to go backward. Here's a z-score formula, or a little bit more practically, n minus center over SD, and that's a z-score. And we know what the center is. It's 62. What is standard deviation? Well, the problem said use the standard deviation of problem 1, 4.95. So we know what to put in here and there. Well, we have it down here. 62 minus 0 and 4.95 respectively. But what's the z-score? We don't know. If we knew all three of them, x minus mu over sigma, we calculate and we can get z-score. But this time it's backward. We don't know what x is, so we cannot calculate the z-score. So what do? We go back to this picture and look at this 25% or 0.25. From that, backtrace the z-table to find out the z-score. Well, here is the normal table. And let's find out, among all those probabilities here, the closest number. We are looking for 25%, so what's the closest to 0.25? Let's see. 0.2514 and 0.2483. These two numbers are the closest to 0.25. Do you agree? And 0.2514 is associated with a z-score of 0.67 And 0.2483 is associated to the z-score of negative 0.68. Which one is closer to 0.25? It's about push. The difference is 0.0014, and this difference is 0.0017. Well, this one is a little bit closer, but I'll call it rather push. So I'm going to estimate it at negative 0.675 or something. So the z-score, I'm going to estimate it as negative 0.675. But as a matter of fact, I use Mathematica to calculate it a little bit more precisely. And my estimation, ballpark estimation, calling those as push, turned out to be a very, very accurate one. The real value is negative 0.67449. So approximating this one as negative 0.675 is actually pretty good estimation. Here in this answer key, however, I'll go back to, what was the previous number? Okay, I'll go back to the previous number, which is a little bit more accurate. If you're using the z-table alone, then you're going to get negative 0.675, but well, I have better figure here because I'm using technology. Why don't I just use a little bit better number here, negative 0.67449. So all I have to do is to solve this equation. I'm looking for the x value, and everything else we have just numbers. So how do we solve this linear equation? Well, first, remove the denominator by multiplying it to both sides. So multiply 4.95 to the left-hand side. It'll kill this denominator. This will be gone. And if you multiply to the right-hand side, well, as you can see, we get something like this. Denominator is killed, and z-score times the standard deviation. You can calculate this one out, but I usually postpone the calculation until toward the end. Well, partly because I'm confident with algebraic manipulation, but another reason is that if you calculate in intermediate steps too often, then you're going to lose some precision, and that's going to cause some trouble later. So it's going to be better if you postpone punching the calculator until the last moment. The last moment is just the next step. All I have to do is just flip this 62.0 toward the other side, and that's what you get. 62.0 minus 0.675 times 4.95, calculate this, I get 58.6613, and that's what this x value, approximately speaking, about 59. So the 25th percentile is about 59 miles per hour. Here's a bit of a justification. What if you put in 59 miles per hour? Okay. Well, it did all the computation here. Never mind, this justification is a little bit tough. I mean, look at this algebraic manipulation. If you understand what this is, great, but if you don't, oh, never mind. Here we go. Let me emphasize again the picture. Outline, center, and okay, let's scroll a little bit further. Outline, center, and then shade. We need 25% in the left. And then z-score. N minus center over SC, it should be the z-score. And we don't know the end value. We want to find out. Center and standard deviation we know. The z-score, we can get it from the table. When you get it from the table, you may have to do some ballpark estimation. And the ballpark estimation was negative 0.675 according to that estimation. A little bit better method using technology was negative 0.67449. Okay, so much for problem 2.